Hello everybody, my name is Boris Zibitsker and the topic of this talk is on cloud decision optimization. At BEZNext we have a team of experts in modeling and optimization, and our current focus is on development of the cloud performance and financial governance software. We also provide services and training for hybrid multi-cloud environment. So what type of cloud-related problems we address? Problems in complex hybrid multi-cloud environment. First of all, uncertainty. Not only technical but business people actively participate in making decisions and frequently use their just gut feelings to make a decision, but they're not sure what will be the result. They have frequently unrealistic expectations in terms of performance and cost. And of course, there is high risk of performance and financial surprises. In reality, response time is not consistent, throughput is not consistent, and cost is going to the roof. So what is our solution? Well, we offer software, services, and training. Our software, BEZNext FinOps optimization software, help in performance and financial governance of cloud environment, which include three phases: understanding operational environment and collecting measurement data, aggregating and providing information about performance analysis, identification of different performance and financial problems. All this information used to optimize, evaluate different options, optimize decisions related to configuration, workload management, to be sure that service level goals for major workloads are continuously met. So this is three areas: inform, optimize, and operate, which in a cloud environment help to select appropriate cloud platform and optimize migration to the cloud decisions, and also help with continuous capacity management of this complex environment. The performance and financial governance process is frequently called FinOps optimization. It includes three areas. One of them inform, which is workload characterization, building performance, resource utilization, data usage profile for each line of business. By the way, this is a very critical component on performance and financial governance, understanding the workload. Then optimize, which applying modeling optimization technology to compare different options and recommend the appropriate solution. Then operate, which is implementing recommendations and providing performance and financial anomaly detection and problem determination. So this is like closed loop control process with feedback control. The most important part of cloud performance and financial governance is use of modeling optimization. So we use iterative queue network modeling and gradient optimization. And the input for our modeling process is information about configuration. In hybrid multi-cloud environment, we have on-prem and multiple clouds, very different platforms with different capacity, with different type of instances used from providers. Then information also about results of workload utilization. For each line of business, we use performance, resource utilization, and data usage profile. Then workload forecasting, information about expected increased number of users and volume of data. Very important service level goals. Sometimes customers have formal service level goals. Frequently they don't. Then doing migration processes or evaluating different options, we assume that the goal of migration to the cloud is to achieve the same level of performance, the same response time or throughput, the same as this line of business is experiencing currently right now on-prem prior to moving to the cloud. And of course, one of the inputs, different options of different platforms, their configurations, instances, and all this information is used as input to modeling and optimization. Let's talk about our approach of using modeling and optimization. So we incorporate queuing network models and gradient optimization to evaluate different options and determine the most effective solutions capable to meet performance and financial goals. And of course, the many factors can affect performance and cost. So look at workloads, and basically multiple workloads running at the same time. Each workload has different profiles, which changing in time, different hours of the day, different activity, different resource consumption, okay, and different configurations. We have so many options from cloud providers, different type of instances. And by the way, allocation of resources and scalability can be achieved by scaling out and scaling up, increase number of instances or increase capacity of the instance or node. There are many different options can be evaluated. Plus, all this evaluation done in hybrid multi-cloud environment where we have workload active using on-prem data warehouse or Hadoop cluster and workload running on different cloud platforms. Okay, and so for each workload, for each platform, we should analyze what's going on hour by hour. And then also take into consideration what will happen when number of users will be increasing, volume of data will be growing. So what do? Well, we perform this type of analysis in multiple steps. And initially we analyze, let's say, proposed configuration and predict what will happen with response time and throughput for each workload during this particular specific hour, and how far our predicted results, predicted performance will be from service level goals. So we find a ratio between predicted response time and service level goals. And depending on this ratio, we determine next step. And all this analysis performed in multiple steps. So we determine what should we do, how should we change our input parameters to be sure that our prediction results for this configuration will be close to service level goals. We find ratio and determine size of the step. Then we defined direction of the next step, and direction based on ratios between each component of the response time and predicted total response time. And the response time has multiple components. It could be CPU service time, waiting for CPU. It could be, let's say, storage service time and waiting for storage, and many others. So the question is how to decide do we need more CPUs, or should we maybe scale out at additional instances or additional nodes? Okay, so we determine which component of response time, okay, is the largest component. So we find a ratio between each component response time and total response time, and it gives us direction. We repeat modeling and predict performance characteristics and compare predicted performance with service level goals. If difference is significant, we repeat this process. and we're making as many steps as necessary until predicted results will be within 1% accuracy difference with service level goals. And we repeat this type of process for first of all, for each workload, for each hour of the day, for each cloud platform. And as a result, we determine the minimum configuration which will be required to meet service level goal for each business workload, sales, marketing, finance, with the lowest cost. This is the most important part of this approach, iterative queuing modeling and gradient optimization. And we use this approach to address very different problems, and we illustrate when we'll talk about different case studies. For cloud selection, for optimizing migration decisions, for capacity management, for DevOps operations optimization. Use practically the same approach, evaluating options and finding option which will satisfy our goal, service level. As a result of modeling and optimization, we provide a lot of valuable information, including determining the minimum configuration and budget which will be required to meet service level goals. When we need more resources, what type of resources, should we scale out, scale up, etc. So a lot of useful information with optimized solution to meet performance service level goals for each line of business, for each workload with the lowest cost. We will review 3 case studies illustrating application of our performance and financial governance optimization for evaluation of different options and finding the optimal solutions during cloud data platform selection, then migration to the cloud, and organizing continuous dynamic capacity management for hybrid multi-cloud environment. The first case study is about cloud data platform selection. An objective of this project is to compare different options and determine which cloud data platform and what is the minimum configuration and budget needed to continuously meeting business service level goals with lowest cost. So problem is that organizations have many options and many factors can affect cloud data platform selection. And selected platform will include cloud provider like AWS, Amazon AWS, very specific cloud data platform, let's say Snowflake, and specific workload which will be supported by this cloud platform, for example, analytic workload and some ETL loading data activity. So from many options, objective is to select cloud provider, cloud data platform, which will help us to meet service level goals, performance goals with the lowest cost. The process of appropriate cloud platform selection includes several standard steps, starting with data collection, then workload aggregation and characterization, then workload forecasting, and using this information is input to modeling optimization engines to evaluate different options and find the minimum configuration required to support business goals. We use information about minimum configuration and public available information about cost of different instances from different providers to predict what will be the cost of meeting business performance goals. This information is used by decision makers to select appropriate cloud platform for the organization. Workload characterization in a cloud, very similar to workload characterization on premises. The difference is workloads are very dynamic and they're changing all the time. So workload characterization process is automated, and we automatically build performance, response time, throughput, resource utilization, usage CPU, storage, etc., and data usage profiles for each line of business, for each workload, on each platform of hybrid multi-cloud environment. Example on the right-hand side is showing just CPU utilization by different line of business. And very similarly, we automatically build resource utilization profile, performance profiles, and data usage profiles. All these three types of profiles are constantly changing for each workload, and different workloads running on different cloud platforms. Not all workloads are moving to the cloud right away. So organizations typically select several workloads, in this case, 4 analytic workloads, which are candidates to moving to the cloud. What else is interesting, by analyzing resource consumption by this workload, we can see that resource consumption during nighttime and daytime, evening time, very different. Obviously, when we move this workload to the cloud, by allocating different amount of resources during different shifts, we can significantly reduce the cost. When we move any workload from on-premises to the cloud, definitely workload will have different profile. So we start with understanding workloads on premises. And this is just example of cluster analysis and segregating all this workload by profiles. In this case, we're analyzing only 2 parameters like CPU service time and kilobyte per query, but actually it could be many other factors which characterize workload profiles. So in this case, we divided all these workloads, which we're moving to the cloud, into very complex queries and very complex workloads, joining multiple tables. Medium type of queries, this is business intelligence workload. And workload with relatively short queries like marketing and sales. So transaction-oriented marketing and sales, and very complex analytic workload finance with joining multiple tables and using a lot of computing resources. So this is very simple clusterizations into short, medium, and complex queries. We also analyze different benchmark tests to collect information on different platforms, and we estimate what is the difference between CPU time or kilobyte per query on different platforms, for example, on premises and different vendors. And we can see that for some of them, CPU utilization in the cloud lower than on premises, for some of them significantly higher. And of course, architecture of different platforms, resources, type of instances used, and database management system optimizers, which effectively use available indices on premises and not necessarily take advantage of available indices in the cloud. All these factors will affect change in service demand for different workloads differently. So we use this information to estimate how service demand of on-prem workload will change after migration to different cloud platforms. This slide summarizing results of modeling optimization and comparing different cloud data platforms. There's a lot of information here, but what is most important, that as a result of modeling, we determined what will be the minimum platform required during nighttime, daytime, evening time, during next 12 months of the year to meet business requirements. So minimum configuration. And they're different during different different time of the day and different during months of the year, because workload will be increasing, number of users will be growing, volume of data will be growing. All these factors we'll take in consideration. And what else is really important here, we have information about estimated budget, how much it will cost to run existing business workloads on different cloud platforms month by month. What is important here, that actually cost of running our candidates, which we're going to move to the cloud, is very different on different cloud platforms. This type of information is used by customer to make a decision about selection appropriate cloud platform. The value of FinOps optimization in cloud data platform selection is in reducing risk of performance and financial surprises by determining the minimum configuration and budget required to meet business service level goals. Organization can select cloud platform and with significant capacity, it will be able to meet performance requirements, but at what cost? So the value here, finding the minimum configuration, just enough capacity to support performance requirements of each line of business during different hours of the day, during different months of the year. And then it definitely will provide the budget which will be required with basically the lowest cost. It provides realistic and verifiable expectations. This case study was done in 3 weeks. And the difference between the actual and predicted results was less than 2%. The second case study is about cloud migration decision optimization. So after finishing selection of appropriate cloud platforms and starting migration, organizations frequently discover that actually they have to support more than one cloud. Different line of business bring different cloud platforms, and very soon it's becoming hybrid multi-cloud environment. So migration plan is constantly changing. So how to finish migration always on-prem workload to the cloud on time and on budget? How to reduce ETL time, loading time, let's say to 8 hours after migration to the cloud? How to predict the security tokenization, detokenization overhead, and additional resources which will be required to support security requirements? What will be overhead of data compression, decompression, and again, how much additional resources will be required to support data compression? How to migrate Hadoop workloads from on-premises to the cloud, and how to make major decisions about migration of Hadoop data lake to the cloud. So this is the problem we address when we use our solutions. After selection of the appropriate cloud data platform and starting migration according to initial plan, very soon organizations discover that actually they have to support different cloud platforms brought by different line of business. And problem of migration and management becoming a lot more complex. They have to migrate on-prem data warehouse workload to different cloud platforms. Some of them will go to Snowflake, some will go to Vantage, some will go to maybe Redshift, and some of the workload will continue using on-prem data warehouse or maybe Hadoop type of environment. So because of constantly changing environment, it's necessary to reevaluate migration plan periodically. And it means the same type of problems we address during cloud selection, we have to address during migration process. And again, we have to figure out how to determine workload candidates for specific cloud platform, how to predict minimum configuration budget required to support these workloads, how to evaluate different options and optimize decisions, and how to measure migration success. This is data loading evaluation example. Graph on the right-hand side is showing pattern of CPU utilization during data load during 1 week. What is interesting, it has approximately the same pattern where significant amount of resources consumed at the beginning of data loading process. And overall, data loading takes 10-12 hours on premises. Objective is to find configuration in the cloud and size of this configuration, which will allow to load all this data within 8 hours. So goal is to predict the minimum configuration and budget required to meet ETL service level goals, load data in 8 hours, okay, or in Snowflake environment. Also take consideration that volume of data will be growing during the next 12 months. According to prediction results, in order to finish ETL workload within 8 hours, we will need 3XL virtual warehouse during peak hour and 4XL off-peak hour. And total number of credits will be 990. So this is configuration, Snowflake configuration, which will be required to finish, reduce batch window for ETL workload to 8 hours. The beauty of modeling that the same type of models and optimization mechanism can be applied to address very different type of problems. So in addition to everything what we discussed, the same type of technology can be applicable for Hadoop migration, optimization, comparing different options migration to Amazon AMS, AMR, or Snowflake, or evaluating tokenization, dataconization overhead to support security requirements, or evaluate block level compression, taking consideration overhead created by block level compression, and predicting what kind of configuration will be required and what will be the cost to support block level compression. Migration to the cloud takes years, especially when organizations decide to support hybrid multi-cloud environment. And different migration options should be evaluated frequently. And beauty of modeling, the same type of models can be used to evaluate different problems. So BEZNext FinOps optimization software helps to evaluate different options, reduce the risk of performance and financial surprises. Third case study is on organizing dynamic capacity management in hybrid multi-cloud environment. And the problem we try to address here is to how to organize continuous data collection, workload characterization, modeling, optimization, how to organize dynamic capacity management process in hybrid multi-cloud environment to continuously meet service level goals for all workloads. The second goal is to how to optimize development and operational decisions during DevOps process prior to new application deployment. So this is the problem we try to address. And what are the major functions supported by dynamic capacity management? Well, the idea is very similar, predicting performance and budget. So dynamic capacity management, this is closed loop process, which includes standard steps, which are performed during all projects with automation of data collection, workload aggregation, workload forecasting, and using information as input to our model and graded optimization engines to evaluate options and find the optimal solution. This minimum configuration which you found during modeling, we used to predict and estimate cost, because each instance which we use as part of our recommendation has on Amazon, on Azure, each instance has very specific cost. So we use configuration requirements or minimum configuration required to meet service level goal to predict and estimate what will be the cost. Okay, And after implementing these recommendations and having expectations, we are comparing actual results with expected and finding the difference, finding the problem. And we continue doing data collection, workload characterization, etc., etc. And this is becoming a closed loop process to be sure that continuously, every hour of the day, every month of the year, service level goals are satisfied. You can select a very specific pricing model, either fixed capacity, flex capacity, or maybe consumption-based model. So we use our modeling optimization software to predict minimum configuration, and depending on variability of workload, we can determine what will be the best pricing model. In this case, we determine that annual cost for this particular environment, the most effective will be flex model, the lowest annual cost. Performance and cost monitoring is critical for organizing continuous performance and financial governance. This example is showing analysis of credit used by different virtual warehouses in Snowflake environment during half a year, month by month, and different color represent different virtual warehouses. And we can see that actually during this period of time, costs significantly increasing. We applied regression analysis against history of credit used to forecast credit used during next 12 months. This is green line. And we also use our modeling optimization algorithms to predict, first of all, what will be the minimum configuration required to meet service level goals, and using these results, estimate what will be the cost required to support service level goals in this environment. So what is interesting, as a result, we have two lines. Green line, this is results of regression analysis, and red line, this is actually results based on Q network models. And red is significantly higher because it takes consideration what type of configuration, what size of configuration will be required to meet service level goals, where regression analysis doesn't take this into consideration. So we have two predictions. One of them is low level, or the second one is high level. So range in predicted cost will be estimation of the budget required to support service level goals. So we have performance predictions and expectations and cost financial expectations for each line of business during next 12 months for different hours of the day. And of course, next step is verification. So this example is showing verification on comparison actual performance results with expected. We have pink line, this is our predicted results or expectations in terms of response time, throughput, and many other characteristics. And we have actual measurement data. So when actual measurement data is significantly higher than predicted, we have a problem. In parallel with comparing actual performance results with expected, we're also analyzing performance and financial anomalies and their root causes, like response time, or total CPU time, total I/O per hour, etc., etc. This is performance anomalies. And financial anomalies is credit used anomalies. So this is example just for 3 different workloads. Different color represent different anomalies, like green is response time, red, this is credit used. So this information about anomalies, we also determine the root causes, and information about situations when actual results significantly different from expected. This is actually identify problems. So all this information is going as input to our prediction and optimization engines to evaluate options and develop recommendations. What should be done? What should be done to fix the problem and what should be done to avoid problems in the future. Our iterative modeling and gradient optimization engines are used to evaluate different options and develop recommendations how to fix problem, how to avoid anomalies, and develop different recommendations and expectations. So in this case, we predict when additional resources should be added to be sure that the response time for this particular workload will be below the service level goals. So we know that during some time, 2XL configuration will be sufficient, and then we need additional resources, and the second part of the year we'll need 3XL configuration to meet service level goal for this workload. The same modeling optimization technology is used for different purposes. This is an illustration how very similar models are used to optimize development operational decisions during DevOps process prior to new application implementation. Here we collect measurement data during testing of new applications and determine anomalies, their root causes, and provide this information to developers. At the same time, we use build models based on measurement results, and evaluate cloud selection options prior to new application implementation. So both developers and operations have recommendations based on modeling optimization technology. So operations can evaluate different cloud options and have realistic information about what will be the cost and budget required to support specific service level goals for new workload prior to new application implementation. In this case, we will see that we will need two 4XL virtual warehouse, which will last from September to December. And then we need 5 3XL virtual warehouse to support service level goals for new applications from January to August next year. Moving forward, our plan to support additional cloud data platforms. We're also doing research how to optimize data and application placement to reduce latency delay for geographically distributed users. So what is unique in our approach? Well, first of all, we developed technology enabling us to organize performance, financial governance, optimization for hybrid multi-cloud environment. And this technology is based on combination of iterative queue network modeling and gradient optimization. We use the same technology based on modeling optimization for different problems which we discussed today, including DevOps decision optimization. And what is the value of this approach? Well, migration to the cloud and managing cloud environment is a very complex problem where many different things affect performance and cost. So ability to evaluate different options and develop realistic expectations, all this reduce risk of performance and financial surprises. This is vendor-neutral approach, and the results of our modeling optimization enable better collaboration between business, finance, and technical leaders. Also, our expertise will help hundreds of Fortune 500 companies in optimizing the usage of their resources. So this is valuable, and also hands-on workshop offering 3 weeks with 3 hours per week of instructions and labs where our participants are solving different problems related to selection of the cloud, migration to the cloud, and dynamic capacity management of the cloud environment. Thank you. and it's time for questions.